have this solution, right? This is the initial solution. When I have this initial solution, what next? What next? I have to test for the optimality test, right? So then I've developed the cost part and calculate improvement index, and this is the result. I found that every empty cell that I'm testing the improvement index, it shows the value greater or equal to 0 for all. So it means I got the optimal solution already. So I'm done. But if you remember that improvement index is mean the value that we can refer to what happened to the transportation cost in total. Positive means you have the cost increase. Negative means you have the cost decrease. So zero, what does it mean? It means that you have the total cost still the same. So in this case, all of them greater or equal to 0, it means this is optimal solution. But for cell 1, 2, it also has 0, right? So it means that if you modify cell 1, 2, the cell that we have improvement index to be 0, you're going to have another optimal solution. For example, I modify cell 1, 2. Do the same way, just previous one. Modify cell 1, 2, and I finish. You can see that I didn't test again because I already got the optimal solution. I just modify cell 1, 2 that have the 0 improvement index. Modify and then I finish. This is another solution. No need to test again, okay? If you test again, just waste your time. Because it's going to show the result for all empty cell greater or equal to 0 again and one cell to be 0. If you modify that cell, you're going to have this solution. Okay? Because it has two solutions, right? And if you have mistake about the calculation, the scary movie gonna start. Right? Because you start from optimal solution, you modify 7 that has 0 improvement index, you have another solution. But you test again and you calculate it's wrong, getting negative, you modify again, you test again, so never ending process, but you're not finished. Starting from optimal solution, if you want to find another one, you just modify and stop. No need to test again. Okay? But it doesn't mean that, for example, you're testing this one, you have this one minus 4. It means that you are not reached the optimal solution yet, right? You need to modify minus 4, not modify 0, okay? Okay? We modify 0 because we want to find another solution. And if the problem didn't ask you, no need to find it for them. Okay? And finally, I want to show you this one. The slide number 60, I think, or that, okay. Just look at this screen. I'm testing this table. I have this solution. All of empty cell here, all empty cells show positive or 0, right? Which means I reached the optimal solution. This is my optimal solution. I'm finished. But if I modify cell 1, 3 from this table, I'm going to have another solution. If I modify cell 3, 1 from this table, I'm going to have another solution. And if I modify cell 3, 2 from this table, I'm going to have another solution. When we combine with this solution, finally we have 4 solutions that have the different pattern of delivered products. But when you calculate the total cost for all of them, it's going to provide the lowest transportation cost equally for all of them. Okay, so in this case you have 4 solutions. So in conclusion, the special case of multiple solutions means you have more than one solution. You can find another solution by modify the cell that we have improvement to be 0. But you can do something like that in the case that you already got the optimal solution first. Okay, and then you modify cell that have improvement to be 0, you can have another solution. If you have 3, 0, you have 3 more solutions. You have 2 zero, you have 2 more solutions. Okay, just this case you have 3 zero, that's why you have another 3 more solutions. So that's why total we have 4. Okay, and the next topic is demand and supply are not equal. Yes, at the beginning, if you remember that I said for our transportation technique, we assume that the capacity side of the factory, remember, and the demand for warehouses have to be equal. But in the world, there is not equal, it's unequal. So how can we do that? Because this is a special case. If your demand and supply in total is not equal, so it's not special case, but we can deal with them. For example, suppose that we have this table. You can see that the total supply, when I sum up here, I have 600. But for total demand, when I sum up the total demand, I have 700, right? It's not equal. So this is special case. But the method that we have studied so far, it requires both demand and supply have to be equally. So then, in this case, it's unequal. So in order to deal with this problem, we just assume that it may to be equal. Assume what? Firstly, you need to consider which side that greater one. In this case, demand 700, supply is 600. Demand greater than supply, right? So it means that you don't have enough product to deliver. So then we assume one more factory. And that factory we call dummy factory. The dummy factory actually does not exist. It does not exist. But we assume that we have the dummy factory and it has capacity 100, equal to the difference between demand and supply. Since the dummy factory it does not exist, so then the unit shipping cost, we just put 0 for all. Because actually it does not exist. Okay, and then we do the same step. Everything. For example, in this case, if I try to find the row or the column penalty for the first column, 2 lowest cost is 0 and 3, so that's why we have 3. The second column 0 and 7, so that's why we have 7. Okay? So if you have demand and supply are not equal, you just assume dummy row or column. In this case, we assume dummy row because demand more than supply. But if supply more than demand, so it means that you don't have enough warehouse, right? So you need to have the dummy column. You have the dummy warehouse or the cost to be 0, right? And this is so. And in this case, finally, if you reach the optimal solution, finally, let's say this is the optimal solution. Let's say you're gonna say that 100 is come from dummy, right? It refers that actually warehouse Northeastern is not getting enough stock because 100 is come from dummy factory. So then it means that actually Northeastern warehouse get the product just 50, right? Like 100. Okay. But by the way, if you don't like the name dummy, you can change it and don't mind. In the past, we have Kitty, Stevie. Okay, so this is second case. The third one, I don't have the example to show you, but I can tell you how can we do that. The third one is called unacceptable route. This means that sometimes we have the problem of, the route of deliver the product that maybe you have the crisis, flood crisis, we have like a protester, just like in Hong Kong or flood crisis in northeastern Thailand. So sometimes you cannot deliver the product because the road is closed or you cannot go that way. So it's called unacceptable route. So how can we deal with the unacceptable route? So let's say that I'm using example, do not see the just look at the table. Suppose that we cannot deliver the product from Bangkok factory to the North warehouse. We cannot deliver product from Bangkok factory to the North warehouse. How can we deal with this? I suggest you that we have two ways. The first way is very simple. The first way is very simple. We cannot deliver product from Bangkok to North warehouse. We all know that the transportation problem is minimization problem, right? So if you don't want to deliver product from Bangkok to North warehouse, you don't want to have any product delivered to this cell. First method is that you just change the unit cost here to be the very big value that significant when you compare all of them. Let's say for me, I can change, maybe I change from 8 to 100. 100 is very big, right, when you compare to another cost. And then you do the same way. Finding the initial solution, testing the optimal, test, modify, something like that. Once you have the optimal solution, no way that you can have any product delivered to this cell because the cost is very high. Okay, so this is the first approach, very simple. Just change the unit cost for the cell that you don't want it to deliver the product to be the very big value. The second way is that easier than the first one, but you have the risk to have mistake. The second way is that, okay, if you don't want to deliver any product to this cell, just pick your pen and mark. You will not consider this cell in every process of your calculation. Initial solution, ignore them. Optimal test, ignore them. Everything that you're going to do, you will not consider that cell. Finally, when you get the optimal solution, no way that you can have any product delivered to this cell. But as I said, it's risk to have the mistake. What is the mistake thing that you're going to face? Based on my experience, you're going to mark just the first table. For the next table, maybe you forgot. When you forgot what happened, you have another problem, right? Then you go. So if you're going to do the second way, I'm going to suggest you, okay, you just mark all table first before you starting doing anything. But because sometimes you mark just only one table and you solve it, and then you duplicate the value to another table, right? But you forget to mark for that table, and then you wrong. So this is the way that we're dealing with the unacceptable rule. Just if you don't want to use this concept, you just change the unit cost to be the very big value, and do the same way. So you're gonna deal with this problem. The last one, before we go to the generation, is called minimization. Maximization, sorry. Maximization means sometimes your problem is be the maximization. For example, if the value in this little cell here is not the unit shipping cost, but instead it's about the unit profit, the problem becomes to the maximization. You will try to find a way to deliver the product from this factory to these warehouses in order to reach the maximum profit, right? Problem becomes maximization. But all the methods so far that we study is minimization, not maximization. But if you have the problem of maximization, don't be panic, just add one more step. Very first step, just using the concept of opportunity cost. Change the maximization to be the minimization by using the concept of opportunity cost. So we're going to change this table, maximize, to another table to be minimization. The way that you're going to change maximize to minimize using the concept of opportunity cost. So for me, I'm looking at the unit cost for the whole table and see what is the biggest value. In this case, the biggest value of the unit cost is 9, right? Unit profit is 9, right? Then you're using 9 minus all the unit profit in the table. So then this one gonna change to 1. This one gonna change to 2, to 4, to 0, to 6, 0, 3, 5, 5, 2, 6, 6. So the table change to be the minimization. And then you follow the very simple step. Finding the initial solution, see? Finding the initial solution. Test the optimality test. Okay, we have -1, you modify and test again. All greater or equal to 0, be done. This is optimal solution. But when you reach the optimal solution, don't forget to bring it back to the original. This is your solution, right? We keep solution, but you change the unit to be the original one in order to calculate the total profit. And that's it. So the maximization, you just add one more step. Change maximize to minimization. Okay, by finding the opportunity cost. Okay, and once you reach the optimal solution, you just change it back to the original value and calculate the total profit. So the exam, I'm guarantee that it's going to be the special case. And normally special case is not come from just one special case. It's combined. It might be the problem of maximization that have unequal demand and supply, and you have some unacceptable route, and maybe you have more than one solution. Don't be panic because we already studied, right? Nothing much. Maximization, you just change to minimization. Unequal demand and supply, you just add dumping row or column. Right? Unacceptable route, you just change the cost. And when you have the optimal solution, you find it 0, you just modify the 0 that has 0, you have another solution. Everything is very simple. Okay, but just be sure that you have the very strong skill of calculation and duplicate the correct one. Right? Because I always see the people, the student duplicate the wrong value. Right? And you cannot finish. The last special case, degeneracy. What is it? Remember that before we do the optimality test, before we do the stepping stone, we need to test the degeneracy or non-degeneracy. So if you're counting the occupied cell and number of occupied cell less than the number of row plus number of column -1, you have the case of degeneracy. When you have degeneracy, if you remember, refer to linear programming, graphical method. Degeneracy means the case that you have 3 constraints cutting at the same point, and that might be the optimal solution. So it's very special. Because when you have the degeneracy case, it means that the rule, some rule, or some concept we cannot apply to the problem of degeneracy. Right? It's a violence, some rule that we cannot use it. In this case as well for transportation, if you have the case of degeneracy, okay, one more thing, transshipment is not covered for our car, just kidding. Okay. Here, the first slide from the last one. You can see this case, we have the degeneracy happening. You can see if a counting number of occupied cell, we have 1, 2, 3, 4, 5, 6. But we have 4 rows. We have 4 columns. 4 plus 4 minus 1, we have 7. So it's less than, right? So it means that you have degeneracy case. For degeneracy case means that for the transportation, they're going to have some empty cell that you cannot draw the closed path. Remember that I said every empty cell you're going to have one closed path. But for degeneracy case, they're going to have like that, some empty cell that you can draw the closed path. For example, if I let you to draw the closed path for cell 1, 4, or say A and W here, cell 1, 4, this cell, you can see that you cannot draw any closed path for this cell. It's gonna lack one more corner. This cell, let's draw the closed path, you cannot draw any. So this is the degeneracy problem. So we cannot apply the rule or the concept that we have studied so far to the degeneracy problem. So if you have faced the degeneracy problem, just like this case, you can see cell 1, 4. We cannot draw the closed path, right? So how can we do that? The way to deal with the degeneracy case that we're gonna assume one corner that we have the number in it, and then we're gonna assume it in order to draw in the cross path, finish the loop, right? But you need to test every possible option. If all possible options that you test show the same result, that the improvement index is greater or equal to 0, it means that empty cell is okay. Improvement is positive. But just only one option that shows the negative value, it means this empty cell is negative. You need to modify. And when you have to modify things, you're going to have some problem, I will show you later. For example, in this case, I'm going to test for this cell. Now I'm talking that I'm going to test this cell that has the degeneracy problem. So I might assume, okay, from this to this to this to this, I assume that I have this one so that I can finish the loop. This is the first option. The second option, I might think that, okay, from here, right, I'm going to this, go to this. I assume this one I have, so I have the second option. So I think it's difficult for you to see, so I'm going to show you again. First one, from this, I'm going to this. I assume that this one I have. Go to loop. No need to lecture because the next slide already have the detail. The second one is might be this one. You go to this, you go to this, you assume that we have this one in order to finish the loop. The third one, maybe you think that you go to this, you assume this one you have in order to finish the loop. Right? So you have three options, I think. If you test these three options, all of them show the positive or 0 for all. We can conclude that this cell improvement rate is okay, positive or 0. But if you have one show the negative, it means that this cell is not okay. You need to modify. But the problem about the modified thing is that you can see here. If you want to modify this one, suppose that they have plus, minus, back, right? Okay, this is one that I said, okay, I have the negative value, I'm going to modify this one. I'm looking at the corner that have minus, right? The lowest value is 0, right? Then you're using 0 plus or minus or subtracting from all the corner, you have the same value. So this is a problem for modifying. So then you need to consider case by case, consider modify every possible things, right? So in conclusion, we're gonna not have degeneracy for your exam. But if I tell you first, so you will not pay attention, okay? No degeneracy for your exam. Because that problem is not that easy and it needs to consider case by case for modify. But this is my word. No degeneracy, my word, okay? When you take the exam, if you finish in the past, I have students, I said, I give you my word, okay, no degeneracy, but when you take the exam, you said that you didn't have the degeneracy, but this is degeneracy, yeah, you know. This is my word. I give you my word. No degeneracy for the exam, okay? So if you saw it and you find this degeneracy, keep it in your mind. You know. For sure, okay? So, no degeneracy for us. Before I let you to make the presentation, let's see this one a little bit. In order to do the case study, what happened here? This is for QM. go to module. It's very easy, no lecture, I think. Go to module and select transportation, right? And then you go to new. For QM, you have no need to develop the dummy for them. They're gonna know if demand and supply are not equal. They're gonna solve for you, and the result gonna show the dummy for you. For example, I'm gonna solve for the problem of unequal demand and supply to show you. Let's say, for example, here, I have 3 factory, 4 warehouse, minimization problem. You just, right, just fill the cost and demand supply, that's it. Oh, sorry. Let's say this is not equal for demand supply. Then you can see here is the starting method. You can select northwest, minimum cost or local, right? It's up to you. Let's say that I select northwest corner. Remember? And then I click solve. I'm getting the result. I click the window to see the result. This is the result. It shows the total cost and it shows the dummy factory. No need to add dummy by your own. QM will do it for you. For others, report is nothing much. We are not using it. Marginal cost, it just show about the difference of the cost for each of the row or column. Nothing much. Final solution table, we're just looking for the number unit that we deliver to. One thing that's very interesting is about iteration. This is show you about how many times that you need to test and modify, You can see if you select northwest, you have 5 iterations before you reach the optimal solution. But if you go back in the data and you select to be local or web, that I said, and you click solve, when you see the iteration, what happened here? You just have 2 iterations. So if you're using northwest, you do a lot for test and modify. But if you're using WAM, you modify just 1 time. Okay, it's better. And the rest is nothing much. It's just show the shipment which cost, show the shipment list. So for the case study, if you're using the QM very fast, just read and you will see the concept. But the case, we have custom brand and Commonwealth ice cream. The case of Commonwealth ice cream is have a little bit finance. So you need to follow through. Case that you're gonna get. Custom brand might be a little bit easier, maybe easier. Commonwealth ice cream is maybe difficult more than the custom brand. Okay, that is all thing that. Okay. So let's make the presentation for your case study. For the example of transportation that we're going to solve together, we're going to practice next class because I want to